from what my colleagues from Romania told me, and my general impression is that CHIAS is really becoming one of the good centers of mathematics in the world. So I'm happy to be here. I will talk today about a not so recent work together with Jean-Marc Schlenker. The title is Deformations or Infinitesimal Rigidity of Manifolds with Particles. So, we invented this term. It's supposed to have some physical meaning. Well, of course, but since I don't know very much about physics, it's not clear what meaning it may have. So, think about a quasi-Fuchsian manifold. And suppose, moreover, that M has singularities along some geodesics, stretching from one copy of infinity to the other. So maybe this should be in a different color. Actually, there is no direction associated to this geodesic. But we think of this singularity as being a sort of particle, and when we look at the formations of such manifolds, we will see the particles moving and maybe interacting. So we also allow we also allow such singularities along a graph. So I should make all this precise. And the basic question is whether such a manifold is rigid, meaning whether you can deform it and under what conditions it becomes rigid. So maybe I should okay.
The conformal structure also has a consingularity in it?
Yes, the conformal structure at infinity will have a conical singularity, right. Okay, so let me first give the model for the singularity. So the model conical singularity, we have, let's say you have hyperbolic 3 space. And you take one geodesic stretching to infinity, let's say a vertical geodesic, and then two totally geodesic planes. And it's like cutting a part of a round apple or orange, and then identifying the cuts to heal the orange. But of course, the customer will see that you took away some of the pieces, right? So V alpha is by definition H3 minus the region between the two you remove what's in between the two half planes, and then you mod out by the rotation with the angle. So if this angle here is alpha, then you mod out by this rotation of angle 2 pi minus alpha. Yes, maybe that the notation is not very good. So rho is this rotation which moves by angle 2 pi minus alpha around the singularity. Let's call D to be this line. Yeah, the singular locus is called D. You cut with two geodesic half planes, and then identify the faces of what you get. This is the typical conical singularity. So the metric on V alpha, you can give so in cylindrical coordinates, here you have x, here you have r, the distance to the singularity, and then the angle around the singularity, you call this variable theta. And then in these coordinates, the metric will be dr squared. Okay, this picture doesn't correspond fully with that. It's just cylindrical coordinates. So you move by in radial directions along geodesics. This looks like a conical metric in one cross section of this cylinder, except that sine hyperbolic is not precisely r. This is the hyperbolic conic metric in 2 dimensions. And then along the singularity, you get cosine hyperbolic squared dx squared. Yeah, so that's how such a singularity should look. And our basic assumption is that all singular angles are at most pi. So the singularity is really up to half what a normal angle should look. Why do we do that? Well, it turns out that when you move such a manifold, the type of interactions that can appear can be quite wild. Namely, two singular lines can collide, or two vertices of the singular graph may also come together to a point. And this is not very easy to control. I mean, singularities get out of control then. So, by doing this, we ensure that the singularities cannot collide. I will explain immediately why. So let me now describe a neighborhood of a vertex. Let's say P is a vertex. Then near this P, we certainly have the function of distance to the P, so we can look in spherical sort of, yeah, again, polar coordinates around P. Let's call this H. So if we look at the distance sphere around P, what we get at time epsilon is going to be a spherical metric, well, with this coefficient sine hyperbolic of r squared. A spherical metric, meaning a metric of curvature 1, but with 3 conical points. Of angles alpha j. This sphere is clearly orthogonal to the singular lines. So when we look at this on this spherical surface around this point, it's kind of clear we get the same conical angle as the cone angle along the lines in hyperbolic space. And then by using Gauss-Bonnet, we see there can be at most 3 conical points. Let's write Gauss-Bonnet.
Alpha is all the same for 3 axes?
No, alpha j. Alpha 1, alpha 2, alpha 3. Right, thanks. Okay, so let's write Gauss-Bonnet for a sphere with conical points. We have integral on this S alpha 1, alpha 2, alpha 3 of the curvature, which is 1. This should give, well, there is also, so this is not a round sphere, it's a sphere like that. So there is curvature concentrated at these points. Plus sum of 2 pi minus alpha j. J is equal to 1 from 1 to n. Let's say we have n conical points, but we'll see n can be at most 3. This should give us the usual Gauss-Bonnet integral, which is 4 pi. 2 pi times the Euler characteristic. Now, this one here should be greater than or equal to 0. And under our basic assumption, each of these numbers is greater than or equal to pi. So there cannot be, actually this is strictly larger than 0, so there cannot be 4 of them, because 4 pi would be then, would not allow Gauss-Bonnet. Good, so I made one proof, usually enough for a talk, but let's see the corollary of this.
You do not allow singularity along close to
Actually we do, yeah, but this is like marginal. It's not a significant improvement. Yeah, so I should make some history of such problems. But let's see first the corollary of this Gauss-Bonnet observation. It says that first there are at most vertices of valence 3, meaning no more than 3 arcs can meet in a point. But also when you do the deformation, that's where it becomes actually more reasonable. When you do the deformation, imagine you have two geodesics which are far away from each other, and somehow by doing a deformation they collide. Well, if the angles are small, this cannot happen. Yeah, because here you would get a point of valence 4. The same thing with two vertices in the graph meeting, then in the end you'd get again valence 4, which is geometrically impossible. So that means that the theory of deformation of such manifolds is reasonable somehow. It makes sense to study them, although maybe we don't need in what we are doing, because we only do the infinitesimal theory. We don't really need so much angle less than pi. We may be able to do 2 pi, but it's a little more complicated, and it's not worth it, because anyway, later on this is the case of interest. Okay. So, as you just said, there is an induced. So far, I haven't really defined the manifolds I'm working with. So I said they are hyperbolic. They may have such singularities, but in some sense, I want them to be convex, co-compact with conical points, and I should make a precise definition of that. Let's first assume that we understand how they look near infinity. So then there is a induced conformal structure with conical points on the boundary at infinity of M. So we have this data, alpha 1, alpha k angles around singular curves. Okay, and then and then I have, let's say, n connected components of the boundary, which are so n surfaces at infinity, each of them with some marked points. Yeah, this is the conformal structure. The mark conformal structure at infinity. It's a Teichmüller space, yes.
Your boundary components is N?
I assume I have n boundary components, and on the first one, for instance, let's say there are n1 ends of geodesics like that, of singular geodesics. So the main theorem I'm going to talk about is the fact that such manifolds are rigid when you fix the angles and the marked conical structure. So it's an infinitesimal result, meaning that the tangent space to the space of deformations is 0. So if we fix the conformal structure at infinity and the angles, then infinitesimally our manifold is rigid. Okay. And as a corollary, we get a local deformation result. So the local deformations, we can parameterize them by the changes in the angles and by the changes in the conformal structures. This will follow by dimension count. Namely, we will compute the dimension of the space of local deformations without restrictions at infinity and on the angles, and we'll notice they are exactly by the rigidity result. We notice they have the same dimension. Okay. Good. So maybe I should start with some. This was like an overview of the result. So there is a let's see. Maybe I should start with the compact case with no singularities. If M is closed and has no singularities, then the fact that you cannot deform the three hyperbolic structure is known as most of rigidity. And we will reprove an infinitesimal version of that. I mean, because we are in the same setting. It's like the zero. Then where M is compact, the singular locus, I will denote by M sub sing this singular graph. When the singular graph is a link, meaning there is just circles, when angles are less than or equal to 2 pi, and moreover, the picture is more complicated than what I said here. There can be the singularities may have also a translation component. Maybe I should not explain what this is because it's not important, and we are not using this as we are not using such singularities. But essentially, okay, I don't, but actually I will. Okay, so essentially here you can rotate you can identify the two faces by the isometry, which is rotation. But you may also rotate and then do a vertical translation, meaning a vertical hyperbolic isometry, which is in fact dilation by some number. And then you identify. So what happens is that you actually will move up. Yeah, so it's not like closing the files of a book, it's closing the files after shifting. And it means that there is a translation component in the holonomy around the loop. So if we allow also an imaginary conical angle, which is this translation component of holonomy, it was proved by Hodgson, Kerkhoff, that there is infinitesimal rigidity. Then I think Bromberg, he extended this case to convex co-compact, meaning that his singularities are still a link in the compact part of the manifold, but he allows funnels. So he proved infinitesimal rigidity by when he fixes the conformal structure at infinity. And then there is a paper by, or a few papers by Weiss. He looked at M compact and singularities along graph and angles less than pi. So he's in our situation, but he doesn't have this stretching lines to infinity, which are supposed to have some physical meaning. Okay, and then I should also say there is a subsequent work using this theorem by Lecuyer and Schlenker, which proved that in the quasi-Fuchsian case with infinite lines, they proved an Alfors-Beers theorem for quasi-Fuchsian M singular with conical lines, angles less than pi. So they're in this situation, only there are no graph points. They are just lines from one copy to the other. And they get therefore they get an identification of the moduli space of such hyperbolic C manifolds and two copies of the moduli space of surfaces with conical points. Okay, so far so much for history. So let's see how one can treat something like that. What is the approach? And I think I'm missing some keywords here. The idea is to identify the tangent space to the space of deformations. To identify it with the first cohomology group with values in some flat bundle E. I think this goes back to André Weil. But I tried to look up his paper, and it's a paper in French from the 50s, and it's like a foreign language, but not the French language. I cannot understand anything of what he's doing there. He's really from another world, like he's too far away. I don't see what he's doing, but that paper is credited for introducing this. I don't see anything. And this approach has been also used by by the other people cited there. So now I think I should introduce this bundle E with flat connection and to see why deformations are in one-to-one correspondence with this cohomology group. And then we can try to apply techniques from algebraic topology, but they don't really work, and then one is led to computing some L2 cohomology. So in this non-compact case, looking at some H1 L2 of this flat bundle will help. So let's see, if you have a phi t isometries, so a one-parameter group of isometries of a manifold M, of a Riemannian manifold M. This means that phi t star G is equal to G, and when you differentiate with respect to t, this implies that the Lie derivative with respect to the infinitesimal diffeomorphism, I mean, with the vector field associated to this one-parameter family. So the Lie derivative of the metric in that direction is 0. So now we write what the Lie derivative of V means, Lie derivative of G, of two vectors. This is kind of elementary. I need this to introduce the bundle E. So this is derivating xy, this function in the direction of V, minus Vx. This is the Lie derivative of x, and minus x Vy. Okay, this is for every vector field. So in particular, this must be 0 for every x and y in V of M. A vector field V like that is called a killing vector field. A killing vector field is a vector field which preserves the metric on the Lie derivative or the tangent vector field to a one-parameter family of isometries. Good. Next, we look at the Levi-Civita connection, or the metric connection. And we compute nabla x v y, where v is our killing vector field. So we notice that this is, if we put a 2 in front of it, this is x derivating vy minus y derivating xv minus xy v. This is a so-called Koszul formula. So I'm just repeating the Koszul formula. And then there are 3 more terms. Plus v of xy plus sorry, let's say minus vx y minus x vy. This is general for every vector fields x, y, and v. But we notice that these last terms are just the Lie derivative of g in the direction of v. These are these terms here. And the first terms are just the exterior. if we look at V as defining a one form by scalar product, this is D of this one form applied to X and Y. Say capital V. Yeah, this is the Cartan formula for the exterior derivative of a one form. Okay, so V is killing if and only if nabla V is equal to 1/2 the exterior derivative of the dual one form. Okay, and we make the following definition. This is all on a general Riemannian manifold. E is this vector field, is this vector bundle, vector fields plus two forms. So du of, let's say, V and alpha. The covariant derivative of a pair made by a vector in the two form is by definition nabla uv plus u contracted by alpha. In the Riemannian setting, this one form is identified with a vector. And nabla v alpha nabla v alpha plus r nabla u, I'm sorry, plus r v u. I hope I got the sign right. Where this is the Riemannian curvature, which is a skew-symmetric endomorphism. So when I apply it to two vectors, yeah, so is it, it's kind of clear how to identify, so RUV belongs to endomorphisms of Tm for each base point, but this is in one-to-one correspondence with lambda 2 of Tm, lambda 2 of M, using the metric G. These are skew-symmetric endomorphisms because of the Riemannian curvature identities. Yeah, R uv x y is equal to minus r uv y x. That's for original metric. Good. So this connection makes sense. Yeah, this is a vector field. This is a one form which makes a vector field. This is a form, and this is also a form. And the basic lemma, I'm not sure, maybe this is due to constant in the 50s. Something like that. Alpha is a two form, yes. It's a one form, but a vector field, right. And I also should say that Tm is in one-to-one correspondence using the metric G with T star M. Yeah, let's say V maps to alpha V, which maps X into the linear one form associated to a vector field is scalar product with the vector field. So yeah, in Riemannian geometry, one usually does not distinguish between forms and vectors. Okay, so the lemma says V is a Killing vector field if and only if the pair V and if and only if this section in the deformation bundle, this is called the deformation bundle, if and only if this section is parallel. So like I construct myself the form component of the section from V, and let's make a definition. This is the canonical lift operator. It's called S from C infinity of M Tm into C infinity of Me. S of V is given by this formula. V minus 1/2 dV ds. Okay, so this is a differential operator of order 1, and the image is parallel if and only if V was Killing. This allows us to study like Killing vector fields in an easier way. So, okay. Yeah, so maybe I should say something about the proof of this constant lemma. It's essentially I mean, it is elementary and essentially obvious, except for one small computation. So what is du of SV? I'm looking at the canonical lift of one vector, so by definition is du of V minus 1/2 dV. Now that we understood the correspondence between vectors and forms, we drop the isomorphism. Yeah? Because d of a vector doesn't make any sense, we know what it is. So, this is nabla V plus, nabla uv plus u contracted with minus 1/2 dV minus 1/2 nabla dV plus RVU. Okay, so let's check that for a V Killing vector field, the first part vanishes, regardless of U. Okay. No, actually, sorry? Yeah, but I don't need that for the moment. I want this term. So I think I made the computation, yeah. So I know what nabla uv is. This part is 0, it's 1/2 dV of u and dot. Yeah, I'm looking at this formula. The 2 gives rise to the 1/2. This one is 0 for a killing vector field. And I'm left with the contraction of this form by the vector in which direction I'm differentiating. By definition, this is 1/2 u contracted with dv. That's what the contraction means. Good, so we see that the first term cancels. The second term is equal to minus, as you said, here is minus nabla u, right? I need to differentiate in a certain direction. Minus nabla u of nabla v. And then this is a small computation. I think one needs to use the first Bianchi identities, or just direct computation, and you check yourself that for V killing, this is minus RVU. So in fact, the second component vanishes as well. Yeah, like you need the first component to vanish, and then yeah. So I will not insist on that. It's really trivial to prove, but it's useful. Okay, so now we specialize to M orientable. Of dimension 3. Then, if V is a vector field, then dV is essentially the curl of V. In what sense? I mean that the Hodge operator of dV, the Hodge star, which maps two forms into one forms, is again this Riemannian isomorphism between vectors and one forms. Yeah, so modulo these algebraic operations, I can identify the dV with the curl. So E becomes just a complexified tangent bundle. And the connection let's call this W now. It's going to be duv plus u cross W. The cross is the operation you learned in high school, the cross product, meaning in three space, and we are always here in Euclidean three spaces. When you have two vectors, you can find yourself a third vector using the orientation and like the area of the parallelogram. So it's more intuitive somehow. This is nabla u W minus u equals V. So I write this in compact form, where phi is a complex vector, complex tangent vector. This is nabla u phi plus I u cross phi, where the cross operation is happening complex linearly in both variables. Okay. Yeah, so we remember this for phi is equal to u plus I W. Okay. Then there is a small remark. the connection, the bundle here is flat. E with the connection D is a flat bundle of dimension 6 if and only if the scalar curvature of M, I'm sorry, is constant. I'm not sure if I didn't make some assumptions here about, yeah, I think I did. When I put this minus sign here, I use the sign of the curvature. So let's say it's constant curvature minus 1, but this is the case which interests us. But the same argument can be carried out for spherical or for flat manifolds. Okay, you have to look in the initial to the translation from the curvature tensor to what you should have here. Good. So you have a flat bundle, and this is another remark. When M is hyperbolic, E is the bundle of infinitesimal Killing vector fields. Namely, E at a point X can be identified with germs of Killing vector fields near X. So not just at X, but near X. It's a little strange. Yes?
Is this only for three dimensions?
What? Here? This works for every dimension, the constant lemma. Now I'm specializing to 3 dimensions. So I think, no, everything works in arbitrary dimension, but you cannot replace anymore 2 forms by vectors. Yeah, n-1 you could, but this vector bundle E is made of vectors and 2 forms in every dimension. In dimension 3, 2 forms become vectors. So you only have 2 copies of the vector fields. Okay, so maybe this is not very clear, but E in fact, okay, over H3, one can do this on any hyperbolic manifold, in particular on H3. Over H3, E is just SL2C cross H3, and D is trivial, the trivial connection. Only that if I give myself an element in the Lie algebra of the isometry group, I can identify it first with the vector field which it generates, and I add to that the curl. So this maps, okay, so if V, let's say, yeah, how should I call that? A is an element in this Lie algebra. I map this into the A on H3. Yeah, the vector field generated by that element on H3, and curl of A. Yeah, so this is the translation between in this language and yeah, this seems easier, but I don't know, for me it seems more complicated. In reality, it's not simple. I mean, you see it's not simple because here is how it goes. Good. So using this bundle E, we are going to describe now deformations. So let's first say M is equal to M tilde mod gamma. So I start with a 3-manifold M, hyperbolic. I lift the hyperbolic metric to the universal cover, and I view M as a quotient by some isometries. Is 1. Good. Then this is a simply connected hyperbolic space. Hyperbolic manifold, I mean. So there are local developing maps a developing map of the metric G defined on M tilde with values in H3. Okay, so I'm not saying this is injective or surjective. It just exists and is defined as follows. So here is this is M tilde. This is a point X. I only draw it in 2 dimensions because otherwise I cannot do that. So this is now H3, and I take a point X prime and the tangent plane, the tangent space at that point. I still draw it in 2 dimensions. So this is Tx M tilde. This is Tx prime H3. I choose isometry this is a linear isometry of 2 Euclidean spaces. Then here I have the exponential map going to M tilde. Here I have the exponential map going to H3. This is a global diffeomorphism. This one we don't know. It may not be, I mean, it may be neither surjective nor injective actually. Yeah, if let me see.
What's the assumption on M?
M is just a hyperbolic. Just a hyperbolic manifold. Yeah. Why don't I take it complete? I don't take it complete because here these lines don't belong to my manifold, so the manifold is clearly not complete. Yeah. So kind of this. I would like something like that to define my developing map. Well, of course, this is only valid in a neighborhood of X, but then it's like analytic continuation. Hyperbolic spaces are like local isometries are generated by just pointwise isometries of the tangent spaces. Yeah, so one can continue this map dev from an open set where it is initially defined to the whole manifold, knowing that it's simply connected. Otherwise, you cannot do that. But since it's simply connected, there is this monodromy property, like for analytic functions.
Not every cone manifold can be written as what's gamma?
Gamma is the deck transformation group. I didn't say anything about it. To prevent objections like that. Okay. Yeah, gamma is pi 1 of m.